So far, we have calculated the electric potential from the electric field. Okay, we use the relation delta V is equal to the integral of E dot dr. Okay, it means that if we are in the region with an electric field, and we want to calculate the electric potential difference from point A to point B along a path, maybe like this. Okay, it means that you do the integration by calculate the E integral of E dr, calculate the EDR along this path, and then add it up to get the potential difference. Okay. So it means that we can say that if we look at, if we pick displacement dr, for example, this one. Okay, it means that we may write this one we may write that dv is equal to E dot dr. The meaning of this expression is that dv is the potential difference between 2 points that is joined by dr. Okay, this is the potential difference between these 2 points, dv, and when we add it up, we will get the total electric potential. Okay, now let's at first see a simple example, that is, if we have an electric field point along the x-axis. Okay, and we want to calculate the potential difference between 2 points along the x-axis. Okay, so when we write down the dr like this, and if the length of the displacement vector is dx, you can see that we have, in this case, E dv, which is equal to E dot dr, is equal to E dx. I forget to put the minus here. Okay, so I have to put the minus sign here too. Okay, so this is minus E dr, which is a minus E dx. Okay, it means that we can write E is equal to the minus of dv by dx. This is the expression that if we know the electric potential, in this case, if E point along the x-axis like this, and if we know the electric potential at any point, okay, on this line, we can get the value of the electric field from the negative of the first derivative of the electric potential with respect to x. Okay. Now, we can see that we can generalize this concept to the three-dimensional problem. That is, if we go back to the general case like this, and we have that dv is equal to the E dot dr. Okay. Which can be expanded as ex dx plus we have minus here, so we have the minus sign here, and this is ex dx plus ey dy plus ec dc, where ex, ey, ec is the component of the electric field along the x, y, and z axis, and the dx, dy, dc is the component of dr along the x, y, and z axis also. You can see that we can interpret this relation that we have dv, which is the summation of three terms like this. So we can say that this is the change of the electric potential due to the change of the position in x direction. Okay. In x direction, and this term is the change of the dv of the electric potential due to the change of the position in y direction. And the last term is the change of the electric potential due to the change of the position in z direction. Okay. It means that if we have the vector dr like this is the dr, and we want to, it means that we want to calculate the electric field, the change of electric potential between these 2 points, which is the dv. But if we resolve dr into 3 components, x, y, and z, okay, it means that you can write down the x component of dr, which is the dx, the y component of dr, which is the dy, and the z component of dr, which is the dc. Now, the first term is the electric potential change when we move from this point to this point. When you move from this point to this point, okay, it is the electric potential change from this to this point. And the second term is the electric potential change when you move from this point to this point. And the last term is the electric potential change when you move from this point to the final point. And as we mentioned earlier that we can calculate the dV which independent of the path. So we can go straight from this point to this point, or we go in this direction first, and then in this direction, and then in this direction. So it means that the first term is the change of the electric field due to the change of the position in this direction. Second term is due to this change, and the last term is due to this change. So mathematically, it means that we can write down that the dE, sorry, not dE, the dx is equal to the minus of dV by dx. Okay. This symbol is a partial differential, partial derivative. Okay. So the partial dV here means is the part of the change of the electric potential due to the change of the position in x direction. Okay. So it means that in this calculation, y and c is taken as a constant. You can see that if we move in this from this point to this point, y and c are constant. Okay, so this is a partial derivative with respect to x, and we can also write that the minus, ey is equal to the minus of the partial derivative of v with respect to y. Again, it means that this is a change of the electric potential due to the change of the position from this point to this point. You can see that along this path, x and c are constant. So this is a change of the electric potential due to the change in the y direction only. So that is the meaning of this mathematical expression. And we can write EC is equal to the minus of the partial derivative of v with respect to c. Okay, and this is the same. This have the same meaning that this is the change of the electric potential when we move from this point to this point. And along this path, you can see that x and y are constant. So it means that if we know the electric potential, you can see that we can calculate the electric field because we can get three components of the electric field. Doing this calculation is sometimes it's much easier than calculate the electric field directly. Anyway, we need to know the v as a function of the position x, y, and z, or v as a function of x, y, and z. Okay, and if we know this, we can calculate the electric field.